Okay, here we are going to summarize the equations that we learned about electricity and magnetism and their connections. Okay, the four equations are summarized under the name Maxwell's equations, and this guy is James Clerk Maxwell, who summarized it. Okay, the first thing, the Gauss law for electricity. Here, the integration of the electric field over a closed surface is proportional to the total amount of charge enclosed in this enclosed surface, which we call also Gaussian surface, right? Okay, and the Gauss law for magnetism, the integration of magnetic field over a closed surface is equal to 0 because the North Pole and South Pole are always together, however small volume you may choose. Okay, and then the third thing, the Faraday's law for induced electric field. The integration of electric field along a closed path is equal to the minus value of the time-dependent change of the magnetic field flux. Okay, and this negative sign comes from the Lenz's law. And you can also equally say that if there is any change, time-dependent change in the magnetic field flux, then it will induce circular electric field in this way. Okay. And the last thing, Ampere-Maxwell's law for induced magnetic field. Here, if you integrate the magnetic field along a closed loop, then it is equal to the summation between two terms. The first term is proportional to the time-dependent change in the electric field flux, and the second term is proportional to the total amount of electric current enclosed by this circular is enclosed by this closed loop. Okay, and then this also means that if there is any electric current, then it will have an encircling magnetic field, and if you have a time-dependent change in the electric field flux, then it will also have an encircling magnetic field. Okay, these are the Maxwell's four equations. They are very important, so please try to remember it. And these four equations, Maxwell's equations, are applied for any electric field and magnetic fields, and which means that they are also applied to traveling waves of electric field and magnetic fields, and it explains how they are connected to each other. Okay, and the way they connected to each other will be explained in the next slides. So now, using Maxwell's equations, we will try to think about the case of traveling electric and magnetic fields and then see how they are connected. Okay, so now first suppose that there is a sinusoidal magnetic field which is traveling along the x-axis, and the magnetic field is pointing along the z-axis. Okay, just like here. Here the blue curve represents the envelope of this traveling wave function. And so, for example, what it means is that magnetic field here is pointing downward, and then is pointing upward here, just like sine wave, and at the same time it is moving to the right. Okay, so it's a traveling wave. So if you want to represent it using the sine wave, then we need the position term and the time term. Okay, so this is what we learned from the spring semester. Okay, and in order to apply the Maxwell's law or Faraday's law of induction, we have to define some small area. So this gray area here. Okay, and then this is a little too small, so we redrew it at the bottom. This represents the same area. Okay, but it's tilted sideways to visualize it better. Now, okay, take a look at the direction of the z-axis. Okay, but this is the same area. Okay, and here what you can see is that in this gray area, on the left side, magnetic field is small, and on the right side, magnetic field is large, right? So therefore, in the bottom figure, we can draw it this way. So if we call the magnetic field on the left side as B, then on the right side, it will be B plus dB is slightly larger. Okay, and at the same time, if this magnetic wave is moving to the right, what will happen to the magnetic flux in this gray area? Looks like it's decreasing, right? So when it's decreasing, according to the Faraday's law of induction and also the Lenz's law, now we figure out that this induced electric field must be going around this square like counterclockwise, right? So in order to compensate for the decrease in the magnetic flux. So therefore, it will go around like the thin arrows here. But then here we don't want to think about it as a circular or encircling electric field, but we want to think about another type of sinusoidal wave. So then now instead of saying that it's going up here and going down, now we can equally say that actually the electric field is strong on the right hand side and weak on the left hand side. Then it will be drawn this way. Okay, so therefore on the left side electric field is E, on the right side is slightly stronger, so E plus dE, right? Okay, and then now let's try to apply this Faraday's law of induction. And then okay, along in this loop, now we are doing the integration of the electric fields. So going around, on the right side is electric field multiplied by the length, which is height h, and on the left side is going down, so therefore it's minus E and then multiplied again by h. So therefore it becomes dE multiplied by the h. Okay, and then how about the time dependent change of the magnetic flux? Of course is minus of d okay, h multiplied by dx, which is the area of this gray square, and then it is now we have to multiply by the time dependent change of the magnetic field, which is dB dt. Okay, and then from here we can actually move this dx to the other side of the equation, and then finally summarize it this way. Okay, so left part is the differential of the electric field with respect to position, and right side is the differential of the magnetic field with respect to time. So we use the form of the partial differential because there are two different variables, time and position. Left side is differential only by position, right side is differential only by time, so therefore it's proper to use the partial differential. Okay, and then now what do you get? If you start by having the sinusoidal magnetic wave, and we can also say that electric field will also become sinusoidal, but then let's try to put it back into the equation we just got. Here for the electric field, you take the positional derivative, so this k, which is the wave vector, wave number, actually has to come out. So therefore, okay, the k comes out here. Okay, and how about magnetic field? For the magnetic field, you take the time derivative, so therefore minus omega has to come out, but there is another minus here, right? So therefore it becomes plus just omega. Okay, and then on the both sides, sine became cosine and cosine. Okay, so you can drop them, and then finally, if you can summarize it, now the ratio between this omega and k is actually the velocity of the traveling wave, according to what we have learned in the spring semester, right? And then let me try to remind you that actually here the position, the wave vector or wave number was 2 pi divided by the lambda, which was the wavelength, and omega was 2 pi divided by the period of this wave. So therefore omega divided by k is actually equal to lambda divided by time. So length divided by time, which was actually equal to the velocity of this traveling wave. And then what we find is that the ratio between these two, which is the velocity of this traveling wave, is equal to the ratio between the amplitude of the electric field and the amplitude of the magnetic field. Okay, and then we will continue on the next slide. Now this time we will think about the same situation using the electric field first. And electric field is now pointed along the y-axis, just like shown here. And these red curves and arrows represent sinusoidal electric field, traveling electric field wave, which can be written this way. Okay, and again this same small gray area, but now this time gray area is perpendicular to the y-axis, because now we want to think about the electric field flux instead of magnetic field flux. Okay, and in this situation you see that on the similarly to what we have seen in the previous slide, the left side of this gray area the electric field is smaller and is larger on the right hand side. So if you redraw it in the second figure, we can now draw it this way. Okay, on the left side, let's call it E, and on the right side is a little larger, so E plus dE. Okay, and then now we will try to use this Maxwell's law of magnetic induction. So therefore, in this case, actually, you can see when it's traveling to the right, the electric field flux in this gray area will change and it will actually decrease, right? So then if you try to calculate this magnetic field going around this loop, actually in this Maxwell's law there is no negative sign, right? So therefore, if the electric field is decreasing, then this value must also be negative, right? So therefore, in this case, if you go around this loop, say using the right hand rule, if you go around counterclockwise and try to calculate it, you will figure out that magnetic field actually must be larger here than here. Okay, so we'll do that. Okay, let's try to calculate it going around this loop. On the left side of the loop, now is B multiplied by H, which H is the width of this area. And on this side, now you are going this direction, but the magnetic field is going that direction. So therefore, as you are subtracting B plus dB multiplied by H. So finally, you get the negative value, right? Okay. And then how about the electric field flux? Of course, this part is just constant. And then in order to get the electric field flux, you multiply the area, which is H dx, multiplied by the time-dependent change in the electric field. Okay, and then similarly to what we had before, now you are moving this dx to the other side of the equation, and then write it using the partial differential. Now this time you are taking the positional derivative of the magnetic field and time derivative of the electric field, which is opposite to what we had before. But nevertheless, okay, let's try to insert these two sinusoidal waves using the sine waves. So for now this magnetic field, you are taking the positional derivative, so therefore this wave number will come out. So therefore you have this, okay, actually you already had a minus sign, so this minus sign simply comes from here, and then the k comes out and sine becomes cosine. Again, for this electric field, you have this constant, same constant, and then when you take the time derivative, now minus omega will come out, so you have minus omega. Okay, and then sine becomes cosine. So finally, you can drop these two signs, minus signs, and then drop cosine, and then summarize. What you get is again the ratio between omega and k. We already know from the previous slide that it is equal to the velocity of the traveling wave, and at the same time it was equal to the ratio between the electric field amplitude and magnetic field amplitude. We had this in the previous slide. So by combining this, what we finally find is that the velocity of this electromagnetic wave becomes equal to the 1 divided by square root of the product between these two constants, which is a permittivity constant, okay, this one, and permeability constant. Okay, does it look a little bit strange? Because when you form these electromagnetic waves, its velocity just becomes a constant, right? So it is a wave which has the constant velocity regardless of its wavelength or frequency. Okay.